In the last video, we made some definitions for Fibonacci heaps, including T of H, which is the number of trees in a root list, and M of H, which is the number of marked nodes. And we defined the potential function to be the total number of trees in the root list plus 2 times the number of marked nodes. And that will allow us to do potential analysis, the potential method. Now, let's look at heap insertion. So we want to take a node, x, and insert it into the heap. And all we're going to do is assume that we already have a heap. We have at least one node in the heap. We're just going to look and see if our key is less than the key. If it is, then we'll make our new node the min node. Otherwise, we're just going to insert it into the heap. Now, you can look at the figure. We're going to insert node 21. So we looked at the min node, it's not there, and so we simply insert it into the root list, and we're done. Constant time for insertion. And if we look at the amortized cost, so that's the actual cost. What's our amortized cost? Well, let's say that H is our input heap and H prime is our resulting heap. The number of root nodes in the resulting heap is equal to the number in the original heap plus 1. We're just inserting 1 into the root list. And we're not marking any nodes, so the number of marked nodes stays the same. Therefore, the increase in potential, or the change in potential, is so we're going to call this delta phi. So the new potential is TH prime, which is equal to TH plus 1, plus 2 times M of H prime, which is 2 times MH, and so those are equal, minus the number of nodes, root nodes originally, plus 2 MH. And that is equal to, well, let's see, this cancels out, and this cancels out. So the amortized cost is, or the change in potential is 1. So what is our amortized cost? Well, it's the original cost plus the change in potential. The original cost we decided here is order 1. So constant time plus the change in potential is constant time. So that's our amortized cost for inserting a node. What about finding the min node? Not extracting the min node, but finding min node. The min node is pointed to by H min. So actual cost is constant time. And the potential doesn't change. We're not adding any nodes to the root list, and we're not marking any nodes. So the amortized cost is the original cost times the change in potential, which is order 1 plus 0 constant time for amortized as well. Now we can unite two Fibonacci heaps or merge or get the union of two Fibonacci heaps. Two heaps. And let's bring up a figure to show that. So here's the algorithm. And again, there's no loop, so it's going to be constant time. All we're going to do is concatenate the root lists together, and those are just linked lists, so we're just going to change a couple of pointers. And then we update the min. Here, we set the min to be the first heap's min, and then if the second heap's min is smaller, then we update it here. And then just update the number of nodes, total nodes, and we're done. So this is constant time as well. And what about the constant actual time? Now what about our amortized time? Okay, so this is going to be our actual time plus our change in potential. Now, what is our change in potential? Well, let's just write it this way to start with. It's our new potential minus, what is our original potential? Well, our original potential is the sum of the potentials of the two heaps that we're unioning together. Okay, so again, order 1 plus, and our new potential is going to be the number of root nodes plus 2mh minus, and then again all of that for each of the Now, notice that the number of nodes in the root lists, we're just concatenating those two root lists together. So we know that TH1 plus the total trees in H2 is going to be the new number of subtrees. And so this right here cancels out with these two right there. So those cancel out. And we're not doing any marking or anything either. So the same thing is going to happen with those. So the total amortized cost is constant. Okay, so that is merging or unioning two Fibonacci heaps together. Now the interesting one, extract min node. Let's bring up a figure. And one more figure. Okay, so what are we going to do to extract a node? So this is assuming that we have a heap, that we have something in the heap, and we're going to pull up each child of the node, of the min node, and add it to the root list. So let's look at the figure. And we have the min node has 3 children, 18, 52, and 38. And we're going to pull those up into the main list, 18, 52, and 38. And so now those are in the main list. So that's what this piece is doing right here. Then we want to remove, change the color here, remove Z from the list. So 3 goes away, and you don't see it in the new list. And then we simply update the min to be the next node. Then we're going to, now notice that that is not actually the min node. That's going to be taken care of here in consolidate. Okay, and we'll talk about what consolidate means. Just to give an idea, consolidate is going to do 2 things. It's going to find nodes x and y in the root list such that the degrees are the same. Then it's going to make y a child of x and increment x's degree. All right, let's look at this graphically and then we'll look at the actual algorithm. So we'll bring up that same figure as well as figure on the next page. Okay. And let's change colors here. Okay, so in A, we're given our original tree. In B, we've taken the children of 3 and we've placed them into the root list and we've removed 3. Now we're going to call consolidate. We're going to first allocate an array of size log n. And actually, it's actually of size d of n, which turns out is bounded by log n. So d of n is the maximum degree of any node in the tree. And so we'll allocate that array and initialize every value to null. Then we're going to start iterating through the array. So we start with this node here, the min node, and we look at its degree and we enter it into the array according to whatever its degree is. So 17 has degree 1, so that's entered in at index 1 of the array. Now we come to part D, and we look at this node here, it's of degree 2, 2 nodes, and so it's placed in the entry in 2, the index 2. Then we come here. Its degree is 0, so it's entered in here. Then we're going to look at the next one, and its degree is also 0. And so we have kind of a conflict here in the array. And so we found 2 nodes that have the same degree, and what we're going to do is merge them. So we take 23 and we make it a child of 7. Since these have to be min heaps, we need to choose which of the nodes is smaller and make that the new root. And so there we go. That's our new node. So we back up to 24. So here we are at 24. And we now look at the next node, 17. It has 1 child, or not 17, 7. It has 1 child, so it's going to be entered in here. And look, we already have a tree with 1 child in it. So we take the max and we pull it into here as a child of that one. So 17 gets moved over here. And then we do the same thing. We back up to 24. We look at 7. It's going to get entered into the 2 children spot. So we need to merge 24 and 7. 7 is going to be the root because it's the smallest. And we add in 24. These are not binary trees. Okay, so now we continue on with 7. It gets entered in with 3 nodes. And we move on to 21. It has 0 children. We move on to 18, which has 2 children. Actually, let's back up. We enter in 18, which has 1 child here. Then we're going to look at 52, and oh look, it has 0 children, so we have a match there. So we're going to move 52 over into 21. Then we'll notice that these 2 match, the 18 and the 21, and so we'll move 21 into 18 to make 21 a child of 18. And then 52 down there. So that's what we get here. Then we move on to 38, which has an entry in 1. And then we iterate one more time and look at each of the new trees, look at the new roots, find the min, and reassign hmin. That's what consolidate does. Let's look at the algorithm itself. So here we allocate A, and we initialize A to be null everywhere. Then we're going to iterate through each node in the root list. And here, while we have a match, so while we have 2 nodes with the same degree, we're going to subsume one into the other. So one match is X, let's use a different color, and one match is Y. We're going to find the smaller key so we know which one to make a child of which. And then we're going to call this fib heap link, which is very straightforward. We're going to remove Y from the list, make Y a child of X, and then update mark. Okay, so we link those, then we set the node at that degree, that particular degree, to null. We increment our degree, and we iterate looking for another node that has our new degree d+1. And then we do that over all nodes. Then all this is doing right here is this is updating the root list and we're also going to update the min. Now we want to know the cost of this. We want to show that this is log n. So we want to show that the amortized cost is order d of n, which is order log n. Remember, d of n is the max degree of any node. Okay, let's look at the actual cost of this operation. Well, we have an order d of n cost where we're moving the min node's children. Let's remind ourselves what that looked like. It's this right here, when we took all of 3's children and moved them up to here to end up with this. So how costly is that? Well, how many children could it have? Well, d of n, we know that we have a bound on the number of children, on the degree of d of n, and so that's how expensive that's going to be. We also have a d of n cost in the array initialization, so in initializing the array A. And A is of the size d of n, so that's why that's order d of n. And we also have order d of n in lines 16 through 23, where we're going to recreate the root list and update min. So our actual cost is order d of n. Now we want to find the cost for lines 4 through 14. And we're going to use aggregate analysis. Actually, we haven't shown this quite yet. We need to find the actual cost of lines 4 through 14 using aggregate analysis. Now, what did lines 4 through 14 do? Recall that here we are, 4 through 14. This is where we're going through and merging trees into each other. And it looks like it's going to be n squared. It looks pretty expensive. This right here, for each node w in the root list h, how big is that? Well, that's t of h. So we're going to iterate on that for loop t of h times. And now we have this nested while loop. And how many times is that going to iterate? Well, you could look at it and say, well, it's t of h as well. It's going to look at all the other potential nodes and potentially merge them. So we have a t squared of h operation. But the key to notice here is how many times can this while loop execute total? Actually, let's write that down here. So the for loop is going to iterate t of h times. The inner while loop, I'm going to claim, is going to run a total of d of n plus th minus 1. So why is that? Each iteration merges one root into another. So how many total merges can we have? We can have only this many total merges. So over the course of all the for loops, the while loop is actually going to end up running only dn plus th minus 1 times. So the actual total time of lines 4 through 14 is order dn plus th. Recall where dn is the maximum degree and th is the number of nodes in the root list. Okay, so that's the actual time. And we can find the actual time of the entire algorithm. So for the whole algorithm, Ci is going to be order dn plus, that was all the previous, and then lines 4 through 14, d of n plus t of h, which is equal to order dn plus th. Okay, so that's actual time. Let's look at potential. Our previous potential was the number of nodes in the root list plus 2 times the number of marked nodes. What's our new potential? That's going to be less than or equal to d sub n plus 1 plus 2mh. This is the size of the array. So it's the max number of roots. So that's the new t of h right there. And here, no, we didn't mark any nodes. So that didn't change. So our amortized cost, finally, it's been a long journey, is C hat of I equals C of I plus the change in the potential energy. So our actual cost is order d of n, plus t of h. And we will add on to that the change in potential, which is d of n plus 1 plus 2mh. So that's our new potential here, minus our previous potential, T of h plus 2mh. That's equal to order d of n plus order T of h minus T of h. And what we're going to do is we're going to get rid of this. We're going to scale up our units of potential to dominate that factor. So what we end up with is its order d of n. And what we haven't proven is that the degree of any node is bounded by the log of n. So it's logarithmic for the insert. That's inserting into a Fibonacci heap. Or not inserting, that's extracting the min value from a Fibonacci heap. Insertion is constant time.